Good evening to all. In continuity of the previous class, we were discussing about a reaction turbine and we have derived the relations for the work done and the power developed. And the power developed expression is given in terms of M multiplied by VW1 plus VW2 whole multiplied by U divided by 1000 kilowatts. M stands for mass flow rate of the steam and VW1 stands for will velocity at the inlet and VW2 stands for will velocity at the outlet, right? Now in continuity of that reaction turbine, now the another relation we are trying to derive is for degree of reaction, right? Degree of reaction. Now we will see what is meant by degree of reaction, right? It is the ratio of the enthalpy drop in moving blades to the total enthalpy drop in the stage. That means stage is from starting to the ending. But what is the ratio? This degree of reaction specifies? It clearly mentions the enthalpy drop in moving blades. That of the ratio of the total enthalpy drop that you have in the entire stage. That means why we call it as an entire stage. Is there any enthalpy drop? Yes, there is a pressure drop from starting to the ending. It is a continuous change of pressure. In the stage, what we have the combination of a moving blade and a fixed blade, right? That means the moving blade, after that fixed blade, after that again moving blade, and after that the fixed blade. It's a series, right? We can go for the multiple stages for this reaction turbine in order to increase the efficiency of the turbine by continuously varying the pressure within the stage, right? The stage means it is starting from the initial point to the end point, and coming to the enthalpy drop means like it is we are going to consider the enthalpy drop over the moving blade and comparison of an enthalpy drop on a moving blade to that of total enthalpy drop that we have in the system. That is the stage, that is from starting to the ending, right? Now we will write the relation here. It is nothing but the ratio of enthalpy drop in moving blades to that of total enthalpy drop in stage, right? Now we'll try to write the relation for enthalpy drop per kg in moving blade. The numerator what we have, we try to derive the relation for this, and for this also we'll write the relation and then compare it and what would be the degree of reaction for an reaction turbine. We'll see that, right? Now enthalpy drop per kg in where we are trying to find in a moving blade. It is represented as H2 minus H3 is represented and given in terms of VR2 squared minus VR1 squared divided by 2. Right? This is the expression for enthalpy drop per kg in moving blade. Okay. Now we will see for the total enthalpy drop in the stage. Okay. The enthalpy drop in stage, as we said earlier, it is from starting to ending. It is H1 minus H3 and it is given in terms of VW1 plus VW2 multiplied by U. Now I have the relation for the enthalpy drop per kg in moving blade and I have the relation for enthalpy drop in the total stage. Now, can I represent these two and get the relation for the degree of reaction? Yes. Now, the degree of reaction equals to H2 minus H3 divided by H1 minus H3. Now, what is the relation I have for H2 minus H3? Vr2 square minus Vr1 square divided by 2 whole divided by what is H1 minus H3? Vw1 plus Vw2 multiplied by U. If I simplify it and try to get the relation for degree of reaction in terms of H2 minus H3 divided by H1 minus H3 is given as Vr2 square minus Vr1 square divided by 2U times of Vw1 plus Vw2. See that? You remember this entire relation H2 minus H3 divided by H1 minus H3 is nothing but this is the expression for degree of reaction. Is this clear to everyone now? Yes. Now we'll take, for example, there are conditions. What would be the degree of reaction for any Parsons reaction turbine? We will derive for this, right? Degree of reaction for Parsons reaction turbine. Okay. Now coming to this impulse turbine, total expansion takes place only in the nozzle. But coming to the reaction turbine, expansion takes place both in fixed blade and the moving blades as well, right? Around like a 50% of this reaction in any of our 50% of this reaction turbine, the expansion of this steam is equal in both the moving blades and the fixed blades. Wherever you find that 50% of this expansion is taking on the moving blade and the 50% of the expansion is being occurred on the fixed blade, that means it is being equally distributed, then we call that reaction turbine as Parsons reaction turbine. Okay, what is the specification? What is the importance of this Parsons reaction turbine? It's a condition like every 50% of expansion, 50% of expansion is seen on moving blade and another 50% of expansion fixed blade. That means it is a continuous process and the expansion is done equally over a fixed blade and a moving blade, right? And now if we try to draw the enthalpy drop, or we will represent it in the turbine as degree of reaction, and then we'll try to derive the relation for this. See, look at the diagram. Here you have both the fixed blade and the moving blade, right? Now, This is the fixed blade, right? Now we'll draw the moving blade. Draw here a moving blade, right? This is the moving blade. Now we have two blades, one is a fixed blade and the second one is a moving blade. Now we try to represent the pressure line. How the pressure will be varying. Starts from here and it gradually decreases to the second point where it is a P2 and it is the initial pressure is P1, and still from here it is gradually decreased, and this is again same P3 and again it leaves out. That means there is a gradual change of pressure from P1 to P2, P2 to P3 over a fixed blade and a moving blade, right? And now we try to represent or draw this enthalpy drop, okay, along x-axis and y-axis. This is your x-axis and this is your y-axis, okay. We will see the enthalpy drop for the concerned pressure lines P1, P2 and P3, right? Here, this is your P1, this is your P2 and this is your P3, right? Now, draw a tangent. Draw a tangent onto line P1. This is the point 1. And the concerned point on the y-axis is represented as H1. This is the pressure line P1. Similarly, can we draw for the second one? Right. Draw the tangent. Now draw the line from the point A so that which intersects the line P2, pressure line P2, pressure line P3 at points 2 and 3. These are the points, right? From these points, draw a line which is parallel to your x-axis and which meets the enthalpy line which is there on the y-axis, H1, H2 and H3. Okay, this is the H3. Now this is the enthalpy drop plot for both pressure lines P1, P2, P3 which are continuously varied, and it is represented in form of an enthalpy drop. Why we are trying to draw for this enthalpy drop? The degree of reaction is defined in terms of enthalpy drop over a moving blade when in comparison to that of a total enthalpy drop in the entire stage, right? And from where to where is your pressure line over a moving blade, right? It is moving blade is here, right? H2 minus H3. That is the reason we have mentioned it. H2 minus H3. From where to where the stage has been initiated H1 and ended up to a point of H3, right? And now this is the reason why we have chosen H1 minus H3. Is this clear? Now we will try to draw the expressions in the next class. Okay, thank you.